This is section 8.4 of your Math Links 9 textbook, solving algebraic equations when there are variables on both sides of the equation. We start off at question 4 where it says, write an equation that is modeled by the diagram, then solve it. So in this particular one, we have the equal signs. We have this expression here. So these paper clips represent x's. So we have 3 x's, or 3 paper clips, plus an additional 15 cents. Now we're going to represent 15 cents not with the traditional 1 5 cent sign, but rather a dollar sign of fractions of a dollar, is equal to 2 paper clips, or 2x, the value of 2 paper clips, plus an additional 30 cents, plus 0.30. So now we have an equation. It says the cost of 3 paper clips plus 15 cents is equivalent to the cost of 2 paper clips plus 30 cents. So if I think about this question in terms of x's, I could also say, this one here. Now, although it's not real traditional, we have a scale to show equality in 3 x's and 2 x's. So if I was to remove 2 paper clips from this side and remove 2 paper clips from this side, or if I think about it in terms of my algebraic modeling, remove those 2 x's and remove those 2 x's. If I think about the balance of that equation once it happens, if I remove 2 of the variables, or 2 paper clips on both sides, it should still maintain balance, which will leave me with this equation. 1x plus 15 cents, or 1 paper clip plus 15 cents, is equal to 30 cents. Now at this point, you probably realize that a paper clip is worth 15 cents. But in order to figure that out, we're going to subtract 15 cents from both sides, or remove the constant. And I would end up with x equals 15 cents. Numerically, here's what it would look like. We would first remove 2x from both sides, creating that algebraic zero pair that we did when we removed 2x from both sides. And if I add 3x and I remove 2x, I end up with 1x. Right? So this is a complete deviation from what we were normally used to, because we would divide to get rid of a coefficient, divide that by 2 to get rid of the coefficient. But here we're actually subtracting 2x from both sides, not to get rid of the coefficient, but to get rid of the entire term. And once we do that, we now have an equation that we're used to. We subtract 15 cents from both sides, and we end up with x equals 15 cents. Or the paperclip value is 15 cents. Question 6 gives us 4 different equations that we have to solve. So just like the paperclip question, instead of having a full paperclip, I only have half a paperclip on the left-hand side, and A is equal to $1.60 plus a quarter of a paperclip. So this gets a little complicated. When you have variables on both sides, what you should do is get rid of it with what you have the least of, or if there's only a variable on one side, get rid of it from the side that isn't there. So I'm going to look at this, and I'm going to say, if I apply a negative 0.25x to a side that has a positive 0.25x, and I do that to both sides, I'm going to subtract that much x from both sides. That creates an algebraic zero pair, leave me with 1.6, or $1.60 on that side. And a positive half of x and a negative quarter of x is going to leave me with a positive quarter of x. Now, if you want to know how to do that, you have to think back to chapter 5 on adding algebraic terms, or adding and subtracting polynomials, I guess is the name of the chapter. And when you are adding or subtracting terms that have the same variable and the same exponent, they're called like terms. And all you have to do is combine the exponents. So technically, I'm going to combine positive 0.5 and negative 0.25 to get a positive 0.25, right? Gathering like terms. And once we have that, we have an equation where we can divide both sides, because this time I don't want to get rid of the entire term. I just want to get rid of the coefficient, and end with x equals, if I take my 1.6, $1.60, 1.6 divided by 0.25, $1.60 divided into piles of quarters. I can make 6 piles and a bit of one, 6.4 piles. So x equals 6.4. In my second question, if I pull it up here, just 1 second, my second question, we have a third of y minus a half equals 1/6 of y. Now, here's what I want you to do. I want you to consider this first. I want you to consider a third of y is the same thing as a third of y, which is the same thing as, if I think about this as being a coefficient multiplying the variable, a third multiplied by y, or if I want to think of the variable as being a fraction y over 1. And when I multiply the numerators, I get y. When I multiply the denominators, I get 3. So it's really, really, really important that you see a third of y, a third of y, and a third of y. All three of those highlighted terms as being the exact same thing. And the reason why that's important is because in this particular question here, what I want you to do is when you have fractional coefficients like we do right here, we have a fractional coefficient. I want you to change that term to this one right here. I want you to change it to a division statement. So instead of a third y, I want you to think y divided by 3, or a third of y, minus a half is equal to, and the same thing here. Instead of saying a sixth of y, through the same process, we can say a sixth of y. Okay. So step one is actually don't do any math. Just change all of those terms to something a little bit more digestible. Because what we're going to do now is we're going to think about this balance of equality, and we're going to think about what would happen if I did this. Would it maintain balance, or would it skew the balance of equality? And the answer is it would maintain equality. And you might be asking, where do I get the number 6 from? Well, in this equation, I have a denominator of 3, a denominator of 2, and a denominator of 6. And one of the cool things about multiplying fractions, if you multiply a fraction, and I'll just take a random one, 3/4, if I multiply it by any multiple of 4, so 4, 8, 12, 16, etc. If I multiply it by any of those, and I'll just choose 12 right now. If I multiply 3/4 by a common multiple of the denominator, I will end up with 36 over 4, which is equal to 9. 9, right? So by multiplying a fraction by a common multiple of the denominator, I end up with a whole number. So if that's true, then if I choose a multiple that 3, 2, and 6 share, so in this case 3, 6, 9, 12, 2, 4, 6, 8. So if I look at the multiples of 3, 2, and 6, the first one they share is 6. It's a multiple of all of those denominators. So if I consider what I just said, by multiplying both sides by 6, each of those terms is going to be multiplied by 6, and because it's a multiple of the denominator, it should become a whole number rather than a fraction. So I'm going to take this side, which is a binomial, there's 2 terms, and I'm going to multiply it by 6. I'm going to take this side over here, and I'm going to multiply it by 6. So what I'm doing is I'm multiplying both sides by 6. Since this is a binomial, I need to utilize distributive property. So 6 over 1, or 6 multiplied by y over 3, will be 6y over 3, or 2y. And if I want to do that a different way, I could just cross-reduce it to become 2y. When I multiply 6 over 1 by a half, or a negative half, I get 6 over 2, which is 3, or minus 3. If I cross-reduce it, I also get 3 anyway. And over here, if I multiplied y over 6 by 6 over 1, I get 6y over 6, or if I cross-reduce, just a y. Now that I have that, I now have variables on both sides. Now I have a decision to make. I can subtract y from both sides, or I can subtract 2y from both sides. It doesn't really matter, but I would probably, normally I say subtract from the side that has the least amount, but I realize that if I subtract y from both sides, I'm going to end up with 0 on that side. So I'm like, you know what? I'm just going to, actually I'm not going to erase the whole thing, I'm just going to erase the y. I'm going to subtract 2y from both sides. And you could subtract y, it's still going to get you the same place, but I'm going to subtract 2y from both sides. So a positive 2y and a negative 2y cancel each other out, leaving me with negative 3. A positive y and a negative 2y, again, if you want to think of it with algebraic symbols, that's a y, and that's a negative 2y. So when we combine those make an algebraic 0 pair, leaving me with negative y, right? And some people think you're done now, but you're not, because technically what we need to do here is we don't want to know what negative y is, we want to know what y is. So I'm going to divide both sides by the coefficient, and y will equal 3. Okay, so that's, in a nutshell, there's a lot of work there, and I showed you a lot of steps because that's the thinking that you need to do to solve that one. But as you get better at it, you would eliminate probably this work here. You wouldn't show all of that work, and you probably, well, the rest of it, I guess you have to show. You might not show, well, you wouldn't show this for sure, and you wouldn't show maybe, well, you would show that, but you don't necessarily have to. You could just rewrite it. Okay. All right, next question. Much easier because we're dealing with the same type of equation, but rather than fractional coefficients and constants, we have decimals. So we're going to say, okay, this is much easier. I'm going to subtract 3.2a from this side and 3.2a from this side. Now, if you added 6.2a to both sides, that's still okay. You're still going to get the same answer. I'm doing this because I know by doing it, I'm left with a value on this side. There's no algebraic term there. And over here, again, I'm combining like terms. So a negative 6.2a and a negative 3.2a, they are like terms. When I gather it, I'm going to combine the coefficients. I'm going to end up with negative 9.4a. And now I'm simply going to isolate the variable by dividing by the coefficient. And I'm going to end up with a is equal to whatever 7.52 divided by 9.4. And I don't need the negative sign because I know my answer is going to be negative. So even though it doesn't say negative, I know it's negative 0.8a. And that's my value. And finally, in D, the last one, we have this fractional coefficient again. And like I told you before I do any work, I'm going to keep that as a negative g equals. I'm going to think of this as 5 halves g instead of 2.5 g. And then I'm going to think of it as being the product of these two, which is going to end up giving me 5g over 2 minus 3. Okay. Now, I have fractions and I have variables on both sides. So what I want to do, and you don't have to do it this way. This is one way you could do it. I could have technically subtracted 2.5 g from both sides, and that's fine. Actually, you know what? Let's do that first. Should we do it that way first? All right, let's do it that way first. Let's do that. So I'm going to subtract 2.5 g from this side, and I'm going to subtract 2.5 g from this side. That makes an algebraic zero pair. I'm left with negative 3.5 g equals negative 3. Okay. Once I have that, I'm like, oh god, I have to divide by 3.5. So I'm going to divide by negative 3.5 to get rid of the coefficient, leaving me with g. And I'm going to divide by negative 3.5. And I'm going to cheat because I know it's fraction form and I don't want to deal with fractions. So I'm just going to go, what's 3 divided by 3.5? I'm going to convert that to decimals. Oh, and I'm going to get this, and I'm like, oh no, I have to keep it as fractions because it's not a whole number. So, all right, here we go. Negative 3. I better give myself a little bit more workspace here. Negative 3 divided by negative 3.5 will be negative 3 over 1 divided by, this is going to become negative 7 over 2. That's negative 3.5. It's going to be negative 3 multiplied by the reciprocal of that, which is going to be equal to positive 6/7. I mean, it's not terribly difficult. But g is equal to positive 6/7. Now, alternatively, so I'll just pause this video if you need to record this, if you want to write down the steps I did for that. Remember, there's more than one way to solve all of these. Really, in algebra, what we're looking for is the most efficient way to isolate the variable, not necessarily, there's not only one path, but there's other paths. So negative g equals 5g over 2. That's what this would become because it's 5 halves g, which is the same thing as 5 halves multiplied by g, which would be 5g over 2 minus 3. Now I'm like, you know what? I'm a big proponent of no fractions whatsoever, so I'm going to get rid of it right away by multiplying this side by 2 and multiplying this side by 2, keeping in mind the balance of power is not going to shift if I multiply both sides by 2. Then that gives me negative 2g equals, and if I think about 2 over 1 multiplied by 5g over 2, I get 10g over 2 or 5g if I cross reduce. So if I cross reduce this, I'd still end up with 5g or 10g over 2, which is still 5g. So 5g, and not only am I doubling this term, but I'm also doubling this term to give me minus 6. Now, it does not take a genius to figure out that this is a much easier equation to solve than the previous one because I have no fractions. So here I'm going to subtract 7g from both sides. And the only reason I did that is because I didn't want to leave 0 on the left. Give me negative 9g, or sorry, why am I subtracting 7g? Why didn't someone stop me? Subtract 5g. And that's going to give me negative 7g equals negative 6. And simply divide both sides by the coefficient. And g will equal a positive 6/7. Same answer, probably a heck of a lot simpler to solve.